thing that I'm hoping to bring to the world is like, we can just go everywhere 3 times faster and at the same price.
You're not building a Scramjet, you are building a Ramjet, but then second stage is just a rocket, basically.
I would never be allowed to fly a fighter jet. So like, I knew I would never be allowed to do that, but I always knew it was like, I could be the one that makes the fighter jets.
Hey everybody, my name's Christian and this is First Principles. Today we're talking to Ian Brooke about the physics and economics of Astro Mechanica, a startup that is building an electric adaptive jet engine. Basically, this would be the most efficient way to launch anything into orbit. The easiest way to think about this is it's either one of the fastest planes ever built or one of the most efficient rockets ever built, or actually it's just both of those things combined. Basically, the way that it works is that you take off from a runway, you drop a payload about halfway through, and then that payload launches itself at hypersonic speeds into orbit. It's an incredibly ambitious idea, and it's actually something that people have wanted to do for a long time. The recent advances that we talk about in this episode have made this uniquely possible today. And so I think you'll love hearing from Ian Brooke from Astro Mechanica here on First Principles. Tell us who you are and what you're building.
All right, yeah. I'm Ian Brooke, build speedy things here at my machine shop, where, build motorcycles, and when I was pretty young, I started from model aircraft and moved into experimental airplanes. And the goal, since the earliest days, was just to build increasingly cool flying machines. And along the way, I think sort of core to all flying machines is like engines and propulsion. That is what defines powered flight. And, we've really been like stuck in sort of different eras of this. So like first there's the piston engines, that was like up through World War II. And, after that we got into the jet age, which is the one we're still in. And sort of neat thing on this is like, we'd call this category like turbo machinery. And, I'd put like rockets in that category as well. They use turbo pumps. And the thing that I've sort of figured out is like, we've had a new technology come about, that's relevant in a sort of a different way that you would expect, which is like electric motors. And this is not for the purposes of like, you don't want batteries. Batteries are not the technology here, but electric motors. And if you use those to augment a turbine engine, you can alter a lot of the characteristics of it, where previously we've had to use different turbine engines for different speeds. So, like turbofans for low speed, turbojet, turbo pump fed rockets. If you instead use like a turbine engine coupled to an electric motor, you can now make one thing behave like all of them. So this is sort of the next era that we're going into. I'd call it like the turbo electric era. If the previous one was turbine or the jet age, everything in flight is like, based on this foundation. And so what we end up with is a new era where any given flying thing can just be adaptive to its airspeed. So we're like, a lot of compromises were needed previously for something to work at a given speed, but now you can make, because of the adaptive engine, you can now have one airframe that can do something like sort of at the limit. If we really mature this technology, you can end up with something of like, you could just fly to orbit essentially, where the engine is constantly changing. Again, it's always that same, just like a rocket, that turbo pump or whatever. It's like that part isn't changing, but all the propulsive components are adapting. And so that was the thing that, I realized is like electric motors got good enough to be used to enable this new thing. So it's not enough to just make an engine, like that's the foundation, but we're actually going to be building the aircraft and everything around this.
No, I love it. But so at the end of the day, you're building an ability to basically take off from a runway and end up in orbit, end up with a payload in orbit.
Yeah, exactly. Yeah. It's using the atmosphere as a ladder to space.
Like that's an awesome way of putting it.
Yeah. Yeah,
and your oxygen tanks and your oxidizer. You're also using it as an oxidizer.
It's all of the things, right? Like if you imagine like a rocket is effectively like, all right, we have to make this thing jump in one leap really high. It's like, well, with this, it's much more like, all right, well, the wings get to use the air to sort of climb its way up, and and then in terms of like powering the whole thing, like it can use the oxidizer around it. Whereas I guess a rocket is a bit more like you're jumping into space while using a scuba tank.
You have to carry all your oxygen with you, exactly.
Yeah. My analogy, this was just like, imagine running a marathon and the only air you could use was in a tank that you had to carry with you. Like that is rocketry, and you need that when you're in space, But sort of the interesting thing is, like, if you look at like Falcon 9 or any of these rockets, that lower stage isn't really actually going that far, if at all, outside of the atmosphere, nor that far beyond the limits of like air-breathing engines. You know, in other words, they're typically around like, you know, so that lower stage, which is like 75% of the mass of a rocket and roughly 75% of the cost, that stage goes to between like anywhere from 50 to 70 kilometers in altitude, and typically they're staging around Mach 6 to 7. And so you can just fly, but you can fly to Mach 5 air breathing. Like, that's about the limit of a ramjet. Then we can go to scramjets, which I am not team scramjet, but yeah.
No, let's talk about it. Let's talk about, like, okay, what's the difference between, like, the fundamental difference between a jet and a turbojet and a rocket, like the basic categories, like what separates those three from each other, and how do they work?
So at their core is this thing, we'd call like the turbo machinery, as I was mentioning earlier. And so what that is you have spinning blades. You're burning something. I call it's like a pinwheel in a blowtorch. You've got your little pinwheel and you're sitting at the blowtorch, and like that part is the same between all of them. One difference with rockets is the thing blowing on the blowtorch. So you're reacting liquids, but still fluid on blowtorch and on pinwheel. So that part's the same, but what changes for all these different engines is how they're generating the thrust. So at low speeds, actually at the sort of the lowest end, you would actually go with even like a helicopter, interestingly. But that maybe sounds a little too weird. So we'll say like a turboprop. You can use a turbine engine. You go through a gearbox and you're spinning a propeller. So you can go from that. Then if you want to go a little faster, you'd go to a turbofan. This is what all airliners use, which is, kind of like propeller, but a little bit smaller. Air goes a little faster through it. And then as we go up sort of the next gear in this sort of speed chart, we would get to, the turbojet cycle, where now, what you're doing is you're not using a fan to just push air. You're instead compressing and expanding air, which is kind of like what the fan is already doing, but you're just doing it. You squeeze it so much that as it expands out the nozzle, it goes supersonic. And that's kind of the difference between like a fan cycle and a jet cycle. It's like fan is sort of like a paddle wheel of sorts of you're just moving air, you're just pushing through, you're speeding it up a little bit, but you're just pushing it through. With jet cycles, you're creating a jet of air where you squeeze it, and an interesting thing happens, which is we have a convergent divergent nozzle, just like rockets, where you squeeze it enough, and as it starts to expand out the nozzle, the wider the nozzle gets, if you compress it enough, as the nozzle gets wider, the air goes faster, and it goes supersonic. So a jet cycle has supersonic exhaust velocity, and that this is in principle the same as a rocket. But rockets, instead of taking air in to do this, they're working with liquid air, liquid oxide, so oxygen and typically kerosene or methane. To both run the thermodynamic cycle of like burning to spin the pinwheel, and then as the reaction mass that they're pushing out. So you can think with like jet engines, we get to have the infinite reaction mass hack. So we're only really looking at like what is the energy in the fuel. But rockets, since again they're sort of limited to this thing they can carry, they're limited to the reaction mass, which is like their version of efficiency is very different for jet engines.
All right, everybody, this is Christian. We're going to get right back to the episode, but first, a word from our sponsor, Secure by Design. In the world of government contracting, cybersecurity isn't an option, it is a prerequisite. You will literally have to fill out forms that assess yourself across all these different dimensions of cybersecurity, and if you find yourself lacking, you have to create a plan about how you're going to get yourself up to compliance. And that's where Secure by Design comes in. Not only do they have decades of experience helping companies with exactly this kind of problem, but they can dedicate their individual people to you on a fractional basis. You don't have to go out there and hire some super expensive executive officer in order to do this. Instead, you can just get a fractional chief information security officer from Secure by Design and use them only whenever you need it. They can help you do maturity assessments against things like NIST. They can assess your compliance with other types of government standards, particularly around cybersecurity. And in the end, they're going to make you compliant for and help you win additional government contracts. With Secure by Design's expertise, you're not only going to meet those standards, you're going to exceed them. So you should book your free consultation call today. Just log on to fedsbd.io. That's fedsbd.io for a free consultation call today. That's perfect. Yeah, so basically, like, okay, I'm gonna go out and let me try to describe it, and you tell me where I go wrong. So basically, in a normal whatever driving a propeller plane or something, like you're just using a motor to spin a blade that's pushing air. That's it. The new thing that we sort of figured out was turbofans, which allowed us to attach basically a turbine to the back of the engine, so like behind the main propeller, which uses some of the forward or like the propulsive movement, not just to like push the plane forward, but instead to turn a turbine, which then turns the fan faster. Like it's basically, it's feeding back onto itself and then being able to, generate more thrust that way. Is that a accurate way to describe a turbofan?
The turbofan is like, you have the fan part in the name, and the turbo just refers to like the source of shaft power. So yeah, it's like, you could have pistons doing this. And so this is like, we just, instead of like, you could run a jet cycle with like a piston engine at its core. It'd be weird, but I think you could do that. Yeah.
New product line for you guys after the.
I am not team reciprocating. I don't like pistons flapping up and down. Not a big fan of that. But I think you could build it.
So turbofans are that, and then basically what a rocket is doing is, instead of having actual like, it's obviously not pushing any air out of its out of the end of the rocket. But what that little propeller is doing is basically just like shoving as much fuel as possible into the place where the combustion is happening. It's like a normal tube wouldn't be enough. It needs a little like thing just shooting as fast as it can to get as much as possible propellant.
Yeah, and it's sort of that's a rocket in a nutshell. It's like you're just squeezing things into a combustion chamber and shooting it out the back. Like, it's like squeezing a hose, right? It's like, where's the pressure coming from? In this case, it's like you put your finger on the tip of a hose, you get that jet coming out. And so the higher the pressure, the more you can squeeze it, the faster it goes. So I guess this kind of segues into maybe some of the points of like, you can consider engine pressure and exit velocity to be somewhat equivalent. So like, again, using that hose analogy, it's like the more you squeeze, like if you have enough pressure behind it, well, you can keep squeezing it more and more, and you're going to get higher and higher velocity of like the jet shooting out. So in the case of rockets, since they're limited in like how much stuff they can carry, the way thrust is mass. It's like the amount of stuff you're throwing out the back times the speed of the stuff being thrown. And so with a rocket, since you're limited, like, well, we only have so much stuff, we have this limited tank. So our best option for high efficiency is we need it to go as fast as possible out the back. And that's why rockets, it's like up the chamber pressure as much as possible. And, that gets very hard at a certain point. This is like SpaceX did this like Raptor. It's like the highest chamber pressure ever. I don't know if it literally is, but it's very high. It's really cool. But that doesn't really apply when you have like infinite reaction mass. That isn't the binding constraint for an air breathing engine, where instead, and this is sort of my thesis on this, is like very antithetical to rocket world of like actually really low pressure. You only want enough pressure to have the air go, like the stuff going out the back only needs to be going faster than you're going forward. And nothing more. Anything more than that, and you're actually wasting energy. So, again, in infinite reaction mass world, it's more about it needs to go just fast enough, but then you want to move as much as possible. So then it's like, this is why airliners, we have these like bigger and bigger engines, because we're trying to move the biggest volume imaginable, which is like literally a physical, it's like if the thing is bigger, you can just move more. So yeah, it's a really different.
And that's what a bypass ratio is, right? Like that's the point of having like, kind of counterintuitively, the more energy from the kind of main engine that you can use to just turn a huge fan blade and just move a lot of air relatively slowly compared to the, as opposed to just accelerating the air as fast as possible. It's actually more efficient. It's more efficient to move bigger chunk of air just a little bit faster, as opposed to a small chunk of air extremely fast.
Exactly. Yeah. This is where, we can probably show like the specific impulse curve of like, that thing you're seeing on that left bound is like, the reason it sort of like goes, asymptotically there is like, you just end up with like, if you had an infinitely large fan, and you're moving it just barely faster. It's like, but you obviously mechanically can't do that. So it's like, and this goes into, so now we start to go into the engineering of this. The constraint that you have is our little pinwheel at the core of this thing likes to spin, pretty fast. I mean, just necessarily so. It's like, you're combusting and you need to extract energy out of it. It's going to spin at some speed. And the problem is that, like, all right, if that's small and the fan it's attached to is big, well, you end up with this this problem of like the fan, the blade tips are going to start to go supersonic. So we have this mechanical limit. Like, we can't actually just make it infinitely large because it's, well, I mean, for a variety of reasons, but it's driven by this thing that needs to spin fast. And so one of the things is like we've made it bigger and bigger and bigger, but we've hit a point where like, okay, the turbine can't spin any slower, the fan can't go any faster. Like, we are designing these things. It's like the really cool, beautiful turbofans we see with that cool swept geometry. That's all to deal with the fact that we actually have the tips of those going, transonic or supersonic. So, along comes like Pratt & Whitney. They make a lot of turboprops, so they're used to putting gearboxes between turbine engines and other spinny parts. And they've created what they call like the geared turbofan. So this was their solution. Is like, okay, well, the speed, the fan wants to, like, we want to make it bigger, but we need to step down the speed. So they put a gearbox between these things. And that, now you have like, we've got a gearbox in here. It's like a mechanically complex thing. It's actually not the end of the world. The reason the geared turbofan is tricky is they've designed this to be a gearbox that's like a lifetime part. So it's like, you don't change the oil in it. You don't, it's like, as it lives as long as the rest of the engine, and it's sitting there, this like really lightweight, compact thing. So anyways, a tough engineering challenge on that. So that was the limit on like bypass ratio. It was like, okay, well, we need to slow it down to have this bigger thing. Then comes like what I'm doing. So instead of a gearbox to sit between these components, what if you put electric motors? So like you instead of having like, imagine like shaft power, spinning gearbox, going to fan, like old paradigm was direct drive. Now we're starting to see a bit more on the the gearbox end of things. But if you can, instead of having shaft power go to, which is like a kinetic energy type thing, if you instead say, actually, we're going to briefly go into sort of the universal currency that is electrons. So we've got our shaft power, and we go into an electric motor to make electrical power. Electric motors are surprisingly efficient. They're north of 98% efficient. So you're not actually losing that much energy in this process. So, all right, we've got our turbine. It's making electrical power. That electrical power then goes over to the fan, where the fan is also driven by an electric motor. So we've, instead of this gearbox and these mechanical couplings, it's now electrical. You can consider once you do that, you sort of end up with like programmable energy. Just like I think a neat way of saying it, but it's just the electrons. They're the electric motor is very flexible in the way that it uses the electrical power you're giving to it. So you can say, hey, actually, spin fast or slow, same amount of power. So you can flow a lot of air through it at a low speed, but it's like huge mass. Or you can flow less air through that fan, but you can have the motor spin up more, pressurize it more. And so now we have this like variability where the electric motor again is just totally flexible in how, how it's utilizing that power. So for this to work, though, this sounds like neat in theory, but the electric motor needs to be really lightweight, because you're replacing what was just like a steel shaft with, both with like two electric motors with all of the things those need to run. And like jet engines are very lightweight and very powerful. And so, as the number I'll give of this is like a fun one, which is like we're using one of our systems is sort of based around like the Black Hawk sized engine, which is it's a 2 megawatt engine, and it weighs about 200 kilograms, so like 400 pounds for roughly 27 horsepower. Pretty good.
It's pretty good.
So an electric motor, like if you were to use a Tesla type electric motor, like pull it out of one of the cars and try and do this thing I'm talking about of like have that between the turbine and your propulsive component. Those are around 2 kilowatts per kilogram continuous power output. Like that's roughly the. So all right, we've got 2,000 kilowatts. So we need 1,000 kilograms. So we went from here's our little 200 kilogram jet engine, and that was just fine. Like it was spinning a rotor, fan, whatever you want. We say actually no. All right, we wanted to spin a generator now. So that generator weighs 5 times as much as the motor, and then we need it again because we need it on the motor end, or the propulsion end. So we went from our 200 kilogram gas turbine, so 400 pounds, to our 2,200 kilogram total mass system. So like you can't go from a 400 pound system to like, I don't know, 4,500 pound system and be like, oh yeah, this is good. Like, no, that doesn't work. So because the other end of this equation is like the thing that you're really optimizing for is total mass, which is to say, it's like weight of the engine and the weight of the fuel, the energy source for it, fuel, propellant. So like, if you have a more efficient engine, so you're going to use less fuel, but if the engine weighs more than the fuel savings, well, then this didn't help at all. And this is like, it's like power plants are very efficient turbine engines, but you wouldn't put that in a,
it's like, oh, we'll just use nuclear power, but like you need so much water or whatever to like actually make it useful, and like that's extremely heavy. You can't just account for like the pure efficiency of the fuel source that you're using. You have to use the efficiency of like the system required to actually get power out of it.
And so this is where we go with like power density, and like so it's not just enough to talk about like efficiency of these things. So that's really what you're really optimizing for is like total weight of the whole thing with the fuel tanks. And this is where like rockets, they're pretty much like they are as efficient as they're going to be. Like the rocket people are tweaking in the margins of the stuff, but rocket is. I always love to give this example of like there is almost the ratio in a rocket of like propellant to rocket is about that of a soda can. It's like 88 to 89% propellant, fuel, and then like a few percent payload. And so it's like, imagine engineering a soda can. You're like, I give you a soda can. I'm like, you cannot add any extra atoms to this. And you need to engineer out of the atoms that I gave you an engine in this thing and all the control systems and all the stuff. And, and then use the liquid in it to fly it to orbit. And, if you're SpaceX and survive reentry, very hard to do. And so they're really sensitive to like the engine has to be super lightweight to work in the system. Whereas in sort of airplane world, it's like, well, our engines, in fact, are so much more efficient that we can get away with, it's like, okay, well, our fuel mass fraction is a fraction of that. So now everything can get heavier. Rather than having like 8% rocket, you can have like, 40 to 50% airplane. So it's a lot more structure that you get to work with. Everything becomes a lot cheaper and easier. But this was the thing, and I sort of glanced over this earlier. Well, electric motors are much better than the Tesla motors now. Like Tesla motors are optimized for being used in automotive. Like they're affordable mass production things. They're not like no doubt Elon could make the most ridiculous cool electric motors if he wanted to, and all the folks at Tesla. But we instead, it's like if you make an electric motor like no compromise, as good as we can get it. We can now get those things not 2 kilowatt per kilogram, but anywhere from sort of the lower bound on the high performance ones are like 12 to as much as 30 kilowatts per kilogram. So, we could just do a 10x on this, right? We could say 20 kilowatt per kilogram up from the Tesla 2. Mm-hmm. And so now, going back to our Blackhawk turbo electric engine system, our 2,200 kilogram total turbogen mass system would now go down to 600. And so that's actually enough where it's like, okay, yeah, 2,200 kilograms, too heavy. 200 kilograms, again, the base turbine is great. But like 600, but it's way more efficient. That system is where it's like, okay, this whole thing actually does get lighter because it is using the fuel more efficiently. And so
just talk about that ISP curve for like, okay, where do turbofans sort of top out? And then what do you have to do once turbofans can't spin fast enough anymore?
Yeah. So we can talking over our ISP curve. So as mentioned, turbofans are a strictly subsonic thing because again, they're just pushing air. They're not. They do a little bit of compression, but they're mostly just pushing air. And so the air coming out of them is not going supersonic. and so the engines can't really go supersonic. So while they're really efficient, they have this like hard speed limit, and we're not even getting the aerodynamics of stuff. We're talking just on the engine. So yeah, they've got more or less a hard stop. This is an act you can do things, but they're subsonic. Then you can go.
Actually, one thing I'll like jump in to say is I don't think people appreciate how close to like supersonic they actually are in like commercial jets. Like commercial jets are going. Well, actually, it's probably like north of 80. It's probably north of like 85% of the speed of sound.
Yes, we use Mach, which is just Mach 1 is just the speed of sound. And so yeah, for airliners, like they've actually gotten a little slower, but some of the good ones are like they're at around Mach 0.8, and anywhere from 0.84 to like 0.86, maybe 0.88. I think the 727 is actually a pretty fast plane, but they didn't use turbofans on those. They used turbojets, but so yeah. Anyways, they're all in the Mach 0.8 range. So yeah, they're
so that's the limit.
Yeah, that's about the limit. And you run into this thing called transonic, that's actually even more the limit. There's like some of the Gulf streams that'll be like around Mach 0.92 to 0.93. Life is getting difficult because like different parts of the airplane they're starting to develop shock waves. So it's like while the plane on average, the whole plane is not going supersonic, airflow over it at different points is. And so like a fun thing on this is like if you're ever on a wide body airplane like a 767 and you're sitting over the wing, you can actually see the shock wave. Like you'll look at the leading edge if you're in just the right spot, and you'll see a little distortion in the wing. Like you just like the air there just looks like sort of a glitch. And so yeah, like that's how close they are at that limit. So then we go to so now we're talking the realm of like, so we want to go faster than that. Well, now we're going to the realm of supersonic. And so you now need your engine to push air a lot faster. Because again, you need to have, so if the thing is going, Mach 0.8, you need the air coming out of it to be going Mach 0.9 something. Or what's for the supersonic, if you're going Mach 1.2, that air's got to be going, 1.4, whatever, some fraction higher. So now we go into that, and now the whole airplane, everything is dealing with shock waves. So, I have like other analogies on this of like, the challenge when you start to deal with shock waves is air can't get out of the way fast enough. So you can imagine like a submarine going through water. Like, you can see them like when they're just coming up and you see like the water all flowing around it. Like that's like subsonic world. Supersonic world is like the air can't get out of the way fast enough. And so you have these like, as we have this like shape. So it's like, as you go faster, you have this like shock wave that forms. It like goes further and further back the higher your Mach. And the engine now has to deal with that. So, we can go to the challenges of like, for combustion purposes, this is one of the things that makes it tricky. Like combustion inside of an engine always has to happen at a subsonic speed. So even, we're going Mach 2 now. Air all around you is going really fast, but the engine, to have combustion occur, because we're not going to talk about detonation engines yet. To have the combustion occur, we have to, we're like scooping air at Mach 2, shockwaves everywhere. Where we need to slow it down now, we need to trade that high velocity for, so as we slow it down, we can trade it for a bunch of pressure, which kind of on earlier themes of like good for exhaust velocity. So we trade it for a bunch of pressure, and we slow it down. So we slow it down to like anywhere from, on the high end, I don't know, maybe like Mach 0.7, 0.8, to the low end, like Mach 0.2. So we're really slowing it down a lot, but we really pressurized it. So we scoop this air in and we slow it down a bunch, and then we heat it up. So we now have this high pressure slow air. We heat it up, and then we do that thing I mentioned of like, now we start to expand it out the nozzle, and then it goes faster and faster and faster again. So it's like, I don't know. I'm trying to think of like, it's like traffic coming up on the Bay Bridge or something of like, you have the toll booth there. It's like, but you're actually...
I was like, finally!
Yeah, finally. You need a bunch of energy, and then like you get on the other side of this thing, you shoot out of there. So that's like what's going on for supersonic engines. So this is a really different process of like this compression, then expansion. So that works well so you use that in the high speed, the supersonic domain. And one of the things is like in the old paradigm, in the world of Concorde and so on, you were always using that supersonic, jet thrust style engine, even when you're going slow. So like this process for like moving air really fast, back to what I was talking about earlier on like rockets with, it's more about energy efficiency, not like mass efficiency as a rocket is constrained by. So you actually just want to move a large mass of air very slowly. And if you're dealing with jet, like a turbojet engine, like again for Concorde, that air is going fast all the time. That engine only has one speed. And that one speed is like, it is a turbojet. It's pushing air fast all the time. So when you're going slow, which is a lot of your flight, like when you're idling there on the ground and you're climbing up, that air is, you're just wasting energy. So like, what's interesting is like Concorde burned, about 40, it's like between 40 and 50% of its fuel between engine start and beginning cruise, which is like wild. And all of that energy loss is just because like you're just squandering it, pushing this air, even though, because the plane isn't going Mach 2 yet, right? But, it's going Mach 0. It's on the ground. So it's just consuming huge amounts of energy to do that. And, so if you, now, the neat thing would be like if you had an adaptive engine, like what I'm working on, it's like, well, at low speeds, we can be the subsonic fan cycle engine. And then as we go faster, we can, it's always adapting. Like the electric motor doesn't care. It just like spins up more and more. We compress more and more. And then we do have secondary combustion cycles behind this once the pressure's high enough. And we need just more thrust. And so like we get to have our cake and eat it too, where it's like, well, it's both of the engines. So that kind of back to that is something of like the engine efficiency or total mass efficiency. It's like, yeah, Concorde is clearly burning a ton of fuel. It's squandering a bunch on this low speed regime. Now, it was really efficient once it's going fast. So, this is like one of the things that's like a little tricky to explain. This is like the adaptive engine, its utility, you can't really examine it at any given point. Like it's not necessarily better than just a direct drive engine at whatever that engine speed is. But over like the whole spectrum, it's like, it's again, thinking of the impulse curve, the adaptive engine is the entire curve. It's not, a point on the curve. So,
yeah. No, that's perfect. I mean, so what is let's talk about Ram versus Scram. Like, so you mentioned that the point of Ram, or like what's still happening in a Ramjet is that you still have to basically slow down the air. So even in a case where you'd be going like whatever Mach 2, Mach 3 or something, like inside it's still going slow. It's still going Mach 0.25 or something, right?
Yeah.
And so the difference between a Ramjet and a Scramjet is that I don't actually know. I think the S in Scram stands for supersonic, but basically it's like it's supersonic while it's moving through the engine.
Supersonic combustion. Yeah.
Yeah.
So yeah, well, using our kind of, if we go into how combustion occurs, so everything we use is we call deflagration. So it's like you're burning, you've got your oxygen and your fuel, your oxidizer fuel, and there's like a wave going through. It's like it's just all reacting, and like they're fighting each other and they're binding and they release heat as they do this. But it's not happening with like a shock wave. So yeah, we need the air to be going slow for that process to occur. Part of this is like, so you say we want to slow it down, and in slowing it down, we get the benefit of the pressure goes up a lot with this. But something that happens is, so we have this thing, adiabatic heating, which is like the more you're slowing that air down, the more you're pressurizing it, the hotter it gets. So like in California, we have like, you actually get to live a neat version of this, which is like, the Santa Ana winds, something like that, where if you have like air from up on top of like a mountain or something, and it goes, so in other words, if we have wind coming from Nevada, it blows air down slope where it pressurizes more, and then everything gets really hot and dry. So it's like, it's always the same thing of like, you have, you're bouncing atoms, temperature being a measurement of like average kinetic energy. You're squeezing it together. They're bumping into each other a lot more. Things are getting hotter. So this process of slowing things down and increasing pressure, you eventually hit a point, and that point's around Mach 5, where the air is now so hot from this, deceleration compression process that it's at the limit of like, it's as hot as the air would be if we burned fuel. So, it's sort of actually a material limit. But anyway, like we make things out of nickel alloys. And all right, we've got this so hot. It's like, well, it's at like, say it's around 1350 Kelvin. Is roughly the temperature you'd be at after, going to like Mach 5 and slowing that down. So it's like, okay, the air before we added fuel is at 1350 Kelvin. Our combustion temp was going to be like, 1350 Kelvin, or, maybe it's a little bit hotter, but still, like, we can't add any energy to this equation. We just slowed it down, heated it up, and that's sort of a problem. It's like, okay, well, we can't go any faster then, because, if we go, say, Mach 6, well, now the air through the inlet is going to be at like 16 or 1800 or whatever. It's going to be getting hotter and hotter. And we just can't, like, the engine will melt. We can't add it into that. Along comes scramjets, which is saying, oh, okay, all right, well, the issue here is we're slowing the air down too much, and it's, causing too much pressure. And like, at first that was great. We wanted that temperature and pressure, but now this is a problem. The thing is getting too hot, and we can't add any energy. So the thinking then goes like, okay, well, what if we don't slow down to like, Mach 0.9 or 0.7 for our combustion? What if we keep it at like, what if we try and like combust this air, and we like, let's keep it supersonic. Let's actually have the combustion occur at that. And that's really hard to do. And so, you can, we've built them, you can do that. And so you get the utility of like, okay, well, we still have the free reaction mass. We're still able to like run this thing faster, but now your combustion efficiency is just going to be much lower. Where when you slowed all that air down to subsonic, it was really easy to get like, not easy, but it was very doable to have all of your fuel and all your oxidizer react. And so you used every bit of fuel, it all translated into energy. Like you can pretty reasonably have like a high 90-something% combustion efficiency with a deflagration engine. Go into scramjet world, and now it's like, all right, we don't know if all the fuel, it's like the air is going so fast now, we don't know if it's all going to react. And so you have to start using other tricks, which is like going into like detonation. So one of the ways to do this is like, hear about RDEs, rotating detonation engines. Like, well, what if instead of deflagration, we do this other thing like detonation, where shockwave, if you ever see like a bomb go, you see like a shockwave going out. Like, what if that's the way that we, have all these things react? And like, it's just very hard to engineer such a thing. And my other critique on this is like, no matter what, going back to our impulse curve, we're quickly approaching the point where the efficiency of the scramjet isn't that much higher than just a regular rocket engine. And when I say not that much higher, it's like, still twice as good as a rocket. But like a ramjet is like 10 times as good. And then, turbofans are, more still. They're like 7,200 seconds of impulse and not more. Versus like rockets at like 360. If you're hydrogen, you're like 450. So yeah, this is the trade-off. And like my thing is like, okay, well at that point, just be a rocket. They're much easier to engineer. And if you're this high-speed air-breathing engine and you're trying to go to space, it's like, well, you're very quickly going to be out of the atmosphere anyways. So my thing is like, do the ramjet. It's really efficient up to Mach 5, and then be rockets from then on. But yeah.
So that's your solution too, right? You're not building a scramjet. You are building a ramjet, but then second stage is just a rocket, basically.
Yeah, exactly. Like, when I was giving the earlier example of like SpaceX and others, where they're staging typically around, they're Mach 6 or 7. So it's like, okay, we're Mach 5. We're like still pretty close to that. But we did need we didn't need to carry any oxidizer to get there. Then you're just rocket, right? So the thing flies right up the limits. It's like it's going as high and fast as it can with like a pretty, like ramjets have been around since the 1940s. It's not like, it's simpler than there's no moving parts in the thing. It's like a jet engine, but you didn't need a compressor or turbines or anything like that. It's just, you're going really fast, you're scooping that air, and you add fuel, and so go faster still. So yeah, do that, and then use like all of the really great rocket engines that have been developed to go the rest of the way to orbit.
Hell yeah, strap a rocket to a plane. So how would the plane need to be huge? Like, does it need? Because I know that there's like straddle launch, for instance, and like the other kind of like start with a jet, but then drop the rocket and let it rip. Like, does your plane have to be massive in order to carry that big of a rocket, or is it just sort of...
No. So straddle launch, the issue with that, like Virgin Orbit, all these things, is that they're staging. They're just using that fan cycle engine. They're only going to like Mach 0.7 or 0.8, back to like their airline type velocity. And so the thing, like, I think you've also said this as well, like, orbit is a velocity, not an altitude. And so it's not really helping you that much to go Mach 0.7. I think Elon was early on, like, talking about this, like, Stratolaunch of, like, it saves you maybe 5% doing what they're doing. And, sort of, Elon's just
for
like,
a lot
okay,
of complexity,
yeah, for, like, all of this extra stuff, you're like, okay, just make the first stage 5% bigger, and you've accomplished the same thing. Now, if you do an adaptive engine, you're talking more in the range of, like, somewhere around, like, 50%, not 5%, but, like, it could actually be as much as, like, 100%, because, again, you can just fly the plane all the way there. So, in our case, though, what we're actually doing is our carrier plane. So Stratolaunch is going to Mach 0.7. We're with our carrier plane. The thing looks kind of like everything sort of looks like Concorde. It's Delta Wing 2, and that's going to go to Mach 2.7, which is sort of like that's like the practical limit of a lot of, like, turbo machinery. Or rather, the airframe. Things aren't getting so hot yet on the airframe that, like, we don't need to worry about it melting. And what you can do at Mach 2.7 is you can air start a ramjet. So SpaceX is, rocket on a rocket. Ours is airplane through ramjet engine. So we got a plane flying on ramjets, and we're going to lower a second stage rocket out of the whole fuselage. Like, all right, lower the second stage, and then you can air start a ramjet. So, like, the rocket now ramjets, they are a jet engine that, again, has, like, no moving parts, but you have to be going, over Mach 2 to start these things. You can actually start them at low speeds, but for them to run efficiently, you want to start them at Mach 2 plus. So our plane's flying along, it's going really fast, and we lower our rocket stage out of this thing, and we air start the ramjet engine on the rocket. Now our second stage is running on, now we just have this thing run up from, like, Mach 2.7 to Mach 5, because we don't want to push the whole plane that fast. It's like, you could do it, but it's like what Hermes.
But everything starts melting, and you hit all the SR-71 Blackbird problems of, like, they're like, I love. So can we do a divergence and just talk about the fastest plane that's ever flown? So, like, that was Mach 3-ish, right? The Blackbird, the fastest it ever got.
Yeah.
And, like, can you just talk about, like, some of the crazy shit that happened with that plane, like the the fuel, like, leaking out of the wings and shit, like, the different material problems. Like,
they had to use, like, corrugated panels because the thing would expand so much. So it's like fun stories of that. Like, there was, like, the first ever titanium airplane, and I don't know what it was, like 92% titanium or something ridiculous like that, which we got from the Russians, to spy on them. The CIA set up, like, companies to, like, source all this, like. So yeah, we didn't really know how to work with it at the time, but it was the only material where it was, like, light enough to fly and could survive these temperatures. So, we had a few other things that, like, your alternative is, like, stainless steel, which is much heavier. Aluminum, in terms of, like, material density, like, aluminum's 2.7 grams per cc. Titanium is, was like 4.5 or so. And then, steel was like 6 to 7, somewhere around there. So much heavier for these other things, but, like, those other ones can survive higher temps. And so titanium is this good in between. You're like, all right, well, it's light and strong, and it won't melt. But then everything else on the airplane is just like life just gets very difficult. In the same way the engine can't survive more than, like, Mach 5, the whole airplane also is not stoked on this. So
that's why you're staging before that. That's why you're getting the plane out of there. Like, basically, you just drop the rocket part of it, basically. The rocket has a ramjet and then also just, like, a normal chemical rocket on it.
Yeah, it's normal chemical. Yeah.
And then, so then the plane just gets out of there and then lets the rocket take the rest of the way.
The plane is going to take 10 minutes from, like, which is much slower than a rocket, but it's like from you're on the runway to that thing is at, 65,000 feet and dropping the ramjet or the second stage. It's like 10 minutes. Now, again, you watch, like, a SpaceX launch, like, that's like a minute or two for it to get to that same point.
Yeah.
But, like, they're really limited in what it has to do that. So we could, like, very efficiently, again, by sort of ladder to space analogy on this, like, we can take our sweet time, our 10 minutes getting there. And then you light the ramjet on the second stage. And that goes for, another minute or two. A lot of trade studies are like, how much thrust do you want to do? Do you want to go that much faster? So, but like this goes into, so there's a thermal limit as we go faster. And part of this...
Meaning, because if you're not out of the atmosphere, you're running into too much atmosphere and you heat up too much?
Yeah, you're heating up too much. And so if you're just not doing it for that long, this is sort of my solution on this. This is why this can work for space of like, all right, well, you can do Mach 5 for like a minute in the air, like as little time as possible. It's like, I don't know, walking across hot coals or something like that. Like, you can do it, just don't stay there. And this is the challenge of like, if you wanted to do sustained hypersonic flight where like you have to stay in the air all the time, that's a lot harder than like, all right, the carrier plane was right in the limit of like aluminum, although we're going to do composite, but like 2.7, not too hot. It can stay there all day long. The thing that it drops is like going to do a quick sprint up to Mach 5. You're like, okay, it's a little toasty. Then you light the rocket and the thing gets to go into space. We're like, okay, no more air. We're not heating up anymore. Yeah. And like in each one of those pieces is like, okay, nothing needs to be that exotic. I mean, you look at like, again, another thing I love is you look at the fairings coming back from Falcon launches. And like those things are coming back anywhere from like Mach 12 to Mach 15. They don't really have any sort of like special heat protection on them. But this is more a testament to have such a low...
It's just the engines. They're just, the engines are just taking the brunt of all of it.
Yeah. But still, like the whole thing is being exposed to like, once you go this fast, you start generating plasma around the whole thing.
Have you seen that video, the one of the fairing returning? It was actually from our launch. So when our satellite launched, that fairing came down. And there's a camera they mounted inside of it, and you can basically just see the like cool like plasma curls like over. It's so crazy.
That was the highest velocity reentry they've ever done on one. For the fairings, because you guys, I mean, it was a really high energy launch going to GEO. GTO. For the GTO transfer. And so like, high velocity launch. And even that fairing, survived that reentry. Now, part of this, again, is it's kind of like, that thing is like Mary Poppins coming back from space, just a big umbrella. It's like, there's not a lot of mass pushing behind it, so it can dissipate it, not get too hot. But, this is like, so for these things that we're building for going up there, you can just minimize the time you're exposed to it. So,
that's awesome. Yeah. What's the overall ambition? So I know that you obviously want to build one of the fastest engines that's ever flown. And you want to build like kind of a new architecture, basically, of a space plane. Like it's not totally new. Like nothing is new in the world where NASA has published these papers from however long ago. But like it's like a novel like implementation of a two-stage architecture. But I think ultimately your ambition is bigger than that. Like you were telling me like you want to build a Boeing.
My goal is like build the next Boeing. If Boeing was like built on the jet age, sort of like they started out in the old paradigm of like B-29s and things like that, piston engines, but they're mostly like a jet era company, and they're also just like an old company at this point. What I really think of this is like we're stuck. It's such a capital intensive thing to make airplanes, like to do all of this. It's so high risk. Again, the stakes are so high. Like it's completely reasonable in a sense to be conservative. Like I love that. It's like really great that you do not need to contemplate the safety of getting on an airliner. Look, people are not stoked on the reason. They do have to contemplate this. People don't like that, right? Like that is not. We don't want to exist in that world. And so, it's like, how do you balance innovation with safety? And it's like, you can go too far on the safety end where like the safest version is like, it's, I guess nuclear energy is sort of example of this. It's like, well, the safest reactor is no reactor. So obviously we don't want that. But you don't want to go on the other extreme of like, I don't know, everybody's like flying around like the most unproven terrifying, like it's like ultralights and stuff like that, where it's just like highly lethal. I personally love motorcycles. They are not safe. Like people should not, that's not a safe way to get around the world. And so, what you need is like a reasonable in-between on this. And that's, SpaceX has proven this as like they've hit the sweet spot of like they are doing new things, but like their engineering is solid. Like it's that sweet spot. And so really, I guess, the thing that I'm hoping to bring to the world is like, all right, there's clearly this next paradigm where we really can have a thing where like we can just go everywhere 3 times faster and at the same price. Like, for the world to feel different, I want to have this experience of like, you're like, a lot of my friends don't like airplanes and things like that. Like, it's sort of convenient to be around. They're like, it's about people getting places. Like, that's like all they really care about. And so it's like, you want to be here in San Francisco and be like, in 4 hours, I want to be in Tokyo. I don't want it to be that expensive. Like, I just want to, they're like Paris, for me, as a Paris, like, I want to get to Paris in 4 hours and not have spent all my money to do it. This should just be like that would feel like the future to be able to do that. And it's like, how do you get to that place? And, all of these things are like, it's many billions of dollars to get there. So, you have to have sort of a long-term plan on this. So if what I want, like everybody's experience with my company in like 15 years, and I think that's about right. I think in 15 years, like everybody will know us for like, we are the one-stop shop company for air travel. And like across all distances. I have plans for subsonic, short range things as well, but like, we're not just making airplanes. Like, we're not an airliner, and we're not Boeing. We're actually a thing beyond that, which is like, we are aerospace. We're making the airplanes and we're operating them. And again, I think it's about like aligning the right incentives where if, again, the point of the plane is to carry people and carry stuff. If our business is selling planes as opposed to operating them, well, this encourages cutting corners on things, making it as cheap as possible, and we're seeing a lot of the effects of this as of late with Boeing. That's not the right incentive. You don't want, so it's like, if I was selling airplanes, I would want to sell them for as much as possible and make as much money as I could on, fixing them. And the only check on me would be other competition. And since the barrier to entry is so high, we see this as like, it's the duopoly of Boeing and Airbus. So we don't want that. That is a bad model, a bad world to exist in. And instead, what if, if like the end value of all of this is people paying for flights? Well, that's the thing that, that's where we make our money then. Like, we should make our money at the most sort of relevant points, for everybody. So start with that. And then the way that we engineer everything is like, so we're paying cost of the airplanes. Like, yeah, we have a slightly higher upfront investment, and this is like higher. So this goes into some of the market risk dynamics of like, it's like, well, you could just sell that airplane for $200 million and not have to worry about like paying, making your money back on the operations or whatever. So like near term, yeah, this could work better. But if we take the long game of this of like, all right, we're operating the planes, we're paying cost of them, so we don't make money, from the plane itself. We're instead optimized to like, we want the thing to be as reliable and safe as possible. We want to get the lowest per mile cost. And like the best way to do that is to vertically integrate. It's like, this allows us to do some other things. So I guess to illustrate how another way that the experience flying with us is going to be so different. We aren't going to be flying airliners. It's not going to be the airline experience thing of everything is going to be private jet sized. And so the better model here is like, if you can have, say, if our cost is roughly a quarter existing, like what it costs Boeing, for the same investment as United into their fleet, we could have 4 times as many aircraft. So when you have a surplus of vehicles like that or airframes, we can afford to have them sit idle. Like we don't, if that asset was really expensive, it's like you need high utilization. And we should strive towards high utilization just to be an efficient company. But we can just have 4 times as many airplanes. So now we're not going to have this thing of like, a plane is only going to fly if people want to fly in it, which is not the current model. Like the flaw of the airline model is this really dated thing of like, back to the 50s and 60s and so on of the, all right, like we've got this plane, we don't have the internet yet. We don't know we don't necessarily know everybody that wants to fly between these places, but we're just letting everyone know we're going to go between San Francisco and New York at like 2:00, at this time, and
every day, no matter what.
Yeah, no matter what. And so you're going to spend that money to fly that airplane no matter what, and it's really expensive. And so your whole reality is like, okay, we need to do whatever we can to fill this plane up to not lose money on the flight that we're committed to doing. The model I'm going with instead is actually we'll have a bunch of like smaller airplanes, and It's only flying. It's like you say when you want to go somewhere, and then like, great, we have a plane for that. It'll go there at the time that you want, when you want, where you want, when you want, and we're only flying it if we're making money. Like, so we instead of the optimization around like, yeah, if we have more people taking more flights, we're just making more money. But if people aren't flying on them, like, all right, no sweat, the plane is sitting idle for a little bit. We're paying cost on the plane. Like that's a much better way to exist. Like it's just going to seem like, planes are just always around to go where you want, when you want. You can imagine it's like being in a city. If you just had tons of Waymos everywhere, it's like you just step out like, oh, sweet, driverless car, we go where we want to go. We're going to have like a flying version of that. And it's going to be, supersonic and getting you there super quick and so on.
So so how do you do the, basically how do you get there? Like, I guess there's so many different paths. I mean, and I'm not saying like, it's so far off or whatever, but what I really mean is like, okay, what you're building is the ability to go super fast, and how you can monetize going super fast is a lot of different things. You could, fly people places. You could fly you could fly satellites into space. You could, whatever, you could do hypersonic testing for the military, like whatever. There's like so many different things you can do with a really fast thing. So how did you decide how you wanted to do it?
Yeah. So yeah, this there's I should almost make another version of our impulse curve over like, so the thing that you want to go with is, so we're starting with space launch because the technology is all the same, but like a fun way to think about this is, what is the dollar per flight? There is no higher dollar per flight thing than sending stuff to space. Usually this is like, roughly speaking, it's like our initial things, say it's like, say we end up going for like a $5 million revenue per flight starting application, like one flight, $5 million. If you were like a Gulfstream, for context, if you charter a Gulfstream, from like San Francisco, like bicoastal San Francisco, New York, that's about $50,000 each way. So you would have to do, 100 flights of that Gulfstream back and forth to make as much money as like one flight of a space launch system. It's like, that's why we're starting there. Is like, all right, we have this new technology. It has this like huge advantage for launching things to space. Well, let's do the thing that just makes the most money per flight. And then you look at other things after that. Like there are like defense applications and so on. It gets a little tricky with a lot of that. Like, I wish it were a free market on those things. Like space is interestingly, like commercial space launch, there's at least like clear path. Like, yes, you get these permits, you do these things, and you get to launch. DoD is a little more like, you have to meet the right person, hope they like the thing. And but theoretically that could also be a pretty good one. But, again, on dollar per flight, you're still not going to beat space launch. So we start there, and say, the market we're looking at, the payloads we can launch with like relatively simple to build hardware. Like, I think our total development cost, put big error bars on this. Like, you could double it or triple it, but theoretically, it could be around $50 million using off-the-shelf airplane parts and like rocket engines and like the parts been special, but with our neat adaptive cycle stuff, sort of stitching everything together. Call it $50 million to develop our initial launch system. And, you're talking about, I won't go into like how low our cost of this would be, but it's much lower than a rocket. So say it's in the range of like, it would probably be around 12 flights, 12 launches to pay back our entire development cost. Like I like that. Those are good economics. Yeah. I'm a big fan of that. Now, like we have a saying in aviation of like, what makes airplanes fly? Money. Money is what makes them fly. So like, if you want to make these cool flying machines, you have to solve you need to make money. And that's a really hard thing to do. So, let's start with this one of like really high margin, make a bunch of money. Then we can, we should fly it more and more. And then we can start to sink the money into, be it drones. Maybe go look at some things like cargo drones, something like that. But I actually think we'd probably just go direct space launch applications. Maybe around, maybe we could do like $500 million a year or so on that, depending on the size of the airframes we're making and how much payload we're launching. But, if you're doing $500 million a year in revenue and like genuinely, you're a real business, you're really making money. I mean, for one, kudos, like we did it. Like this is great.
Yeah.
But now, the cost to develop an initial private jet size thing, like if we want to do this V1, a thing that you get to take around, we want to go for that Gulfstream market. That's, people would have, we could debate, I guess, like where the cost would be. Like, let's say it's like $5 billion. For context, it's like most private jet programs are somewhere in that range, anywhere from like lower bound $3 billion. If you could be upwards of like $7 billion for like Gulfstreams, things like that. And then airliners, if you like 787 program, those are like 20 to 30 billion. So let's start with like the small, it's supersonic though, and this is sort of the unknown components. Like, can we say if the technology is simple enough, could we say this is going to cost the same as like a Gulfstream to develop? I actually think it's, for one, I think we have a whole bunch of manufacturing. Like, we're coming from a place of we've been making and operating space launch vehicles.
Right.
So we learned a lot of expensive lessons. That's part of why I think this $5 billion number is like plausible. It's like we sort of subsidized it in a way of like we learned a bunch of the expensive lessons already in this cheap to learn space of space. So start there. And then that thing is like, okay, we have the sort of Gulfstream, like we're going much like the Tesla Roadster. We're going for like the wealthiest, those people that are paying $50,000 on the Gulfstream, like, hey, we can get you there. That 6-hour flight's 2 hours now. And instead of like $50,000, hey, it's $80,000 for this flight. But again, that much faster. And, like there's only, probably a couple hundred people that are willing to do a thing like that. But like, much like with the rockets, like you're making so much per flight. That's all you need. Yeah. So now you've got this, like, okay, we've got a large, charter fleet for like private jet type stuff. And we've consumed everybody that's willing to like pay those crazy prices. Now you're in the position of like, so it's like step one, rocket company, highest revenue per flight. Then we go for like the wealthiest and like the private jet in the world, I don't know, like maybe it's like flying CIA agents around and stuff like that too. Who knows? really mission critical, expensive stuff there. Then you can go the next step of like, okay, let's go for like the 30 passenger regional airliner size thing. And there's a reason also I say 30. It's this thing Part 380 of the FAA. There's a company Jet Suite X that uses this particular, it's not a loophole, but you are not an airliner if you're under 30 passengers. You're a charter.
So JSX is not an airliner?
No.
You're charter plane. Wow.
There's two things. So they're Part 130. It's two entities. There is you have a travel agency, and then you have a charter operator. So one is the company that operates the aircraft is Part 135 charter, and the other one is the one that does the bookings and so on. So we would be going for a similar if you're small enough, you don't need to have these two entities. I think it's more like 19 passengers. And then this is another thing. This is also moot if you're doing unscheduled. This is what allows Jet Suite X to do scheduled flights.
Yeah.
But kind of my whole point is like, I don't know, I think we can get away with not doing that.
Cool.
So anyways, yes. So we do that. It's like, I don't know, somewhere between like 4 to 8 passenger small thing, loosely based on our initial space launch vehicle. Those things are like similarly sized. We learned a lot of the lessons on, data on engine reliability and so on, pushing to a more extreme environment. Then we make our bigger version. And then like this one is like, so the first one is like catering to private jet class people. Then we go for business class travelers. That's sort of the 30 passenger version where, it's like, and then finally after that, then you would go for the full, then we will have to just make, at some point it does make sense to have the airline style model. For like the really common city pairs, again, of like, San Francisco, Tokyo, or whatever. And then that would be like 100-person, Concorde-ish thing. But we'd still be paying cost on them. We'd still aim for having a bunch of them. So that's sort of like, and then that's the one where you're now down to like that thing can be cheaper per passenger mile than even subsonic airliners. And I think I sort of glanced over all this is the fuel that we're using is not jet fuel. All rockets are switching to methalox. Methane in LNG, same thing, more or less. So that's about 1/10 the price of jet fuel. It's the simplest hydrocarbon, and if you're worried about environmental things, it's also the easiest hydrocarbon to synthesize. So you can do, I think we both know like Casey Hammer, Terraform
Casey,
Industry.
yeah, exactly.
Big fan. you can do direct electrical into chemical energy, and like the CO2 that is being held in the hydrocarbon fuel, you pulled out of the atmosphere electrically. And so even with that, you're still, an electrically derived methane fuel is still around a fifth the cost of jet fuel out of the ground. So carbon neutral, everybody gets to go fast. This is very much like the accelerationist, like, let's just use more energy. So long as that energy isn't coming with like an environmental impact, there's that, like, if you eliminate that component, you can just use more. So
yeah,
that's the long arc of this, like space launch to bougie private jet to business class traveler to everybody. And we are fully vertically integrated as a company. Like, we are the manufacturer and the airline and all the things. You just go to us. And then we have other solutions like our same hybrid, our expertise with this hybrid architecture enables us to make something like a V-22 Osprey considerably safer. The gearbox is the sketchy part of a V-22 Osprey. So if you can make an Osprey that doesn't have a gearbox, like, you don't need to do the silly flying car shenanigans. Just do Osprey, no gearbox, and use turbine engine, and you can just have a thing now where this is like the final piece sort of our thing of like, if you want to do SFLA, well, have a barge in the bay or an airport, whatever. But like, most population centers are on the water, so I actually kind of like this idea of like, own your own little, it's like barge aircraft carrier type thing.
Yeah.
And so like, you just tell us where you want to go. Like, all right, well, if it's short haul like that, we use the thing where you don't need to go to the airport. You just go to the nearest one of these like pad areas, and that goes 300 knots, so that's going to do LA in an hour. So start with those. That's like your smallest, like, shortest range unit. And those things, a requirement of anything that's going to carry people to be safe. This is also where I diverge from the flying car people. If you are not, at least 25,000 feet, you want to be going 250 knots and 25,000 feet at minimum. And ideally, you're more like 30,000 feet, 300 knots. That's the threshold for safe, reliable passenger transport. If you don't hit those criteria, you're not safe. For the reasons of
meaning you're too low, and you're not. Like, you don't have enough time if something goes wrong.
Yeah, your terrain is too much. Like, the weather and terrain will impact your flight too much. Where like the simplest solution, like this is how airlines function, is like, just go up and over it, and it doesn't matter then. So that requires a certain base level of energy and performance. But so design around that, like, you can make the thing that does that, and it is affordable to everybody. Back to the sort of, you can make the V-22, like the efficient V-22. So that's like our final. And at this point, we like, you can see how we eventually get to the point of like, we are just aerospace, right? We've got like space launch all the way through, and like, that's how you build the next Boeing. You're just going very incrementally, like any one of these steps. It's like, okay, we're doing the $50 million, the like space launch program. That makes our, $500 million a year. Then we can go to our $5 billion program for doing the first private jet. Then you can go into, all right, maybe it's like 10 to 15 to do that 30 passenger program, or maybe not. We'll learn lessons. We'll see how affordable we can be on this. I think, like, for context, SpaceX has spent $5 billion, and I think it'll be probably around like total is the expected spend on Starship. For Falcon 1, it was about a $90 million development cost. So this is when I say it's like $50 million.
That's amazing.
This is partly, they are an incredible organization. Like, that is a level of competence. Like, you need to be really sharp to do that. But I would argue, like, our stuff is actually simpler. Like, that was really hard to do. I'm using off-the-shelf jet engines. And, like, we're going a little more easy mode. But, and it was also inflation. I don't know, that was early 2000s when that was happening. But still, Falcon 9 total development was around $300 million ish. And then you go to like Dragon and so on. Like, there's a neat report that like NASA corroborated a bunch of these numbers and like, that was about the cost of these things. So this is how I actually feel okay on our initial starting costs. Again, we need to be diligent on this, but then we'll see again on these bigger programs. Like, I actually think that, if we can bring that sort of efficiency to these bigger programs, they don't have to be expensive, but it is important. Yeah. Okay.
Let's dive into that though. So I think that's a perfect segue into talking about the sort of organizational piece of it, because I know this is something you really care about. I know this is something you've thought a lot about. Basically, like, how do you make an engineering organization that doesn't become slow and, you know, too safety or like too like risk averse and like actually, you know, delivers cheap products? Because you can't just will cheap products into existence. You have to have an organization that, you know, has the right DNA to actually go do it.
Yeah, I think this is my inclination and methodology on this is, it's definitely not. It's like buy once, buy right. I'm pretty big on this of like again, different schools of thought. Some just go for like just make the thing so cheap. I'm much more inclined towards like build something that you never have to worry about. Like, airplanes, they fly so much that they're far more dominated by initial acquisition cost is much less relevant than total operating costs. Like, if you just engineer something where like it just doesn't break, all of our favorite things. There's a reason everybody loves Toyotas. Like, they, this, like, I guess it's sort of an example of this. Like, I love German things, but German cars, like, you look at their philosophy, like, they get a lot more out of what they have. But this comes at a cost of, like, they're a little more finicky. Where, like, Toyota, famously, there's, like, the Toyota Supra is, like, an example of this. Like, everyone always talked about, like, the engine that was in that car, you didn't have to do anything to it, and that engine could deal with, like, 600 horsepower. You didn't have to, like, so in other words, they were just, like, hugely, like, they do this with all their stuff.
Yeah.
Toyota Tacomas, same thing. That engine, it gets, like, they don't push thermal efficiency that high. They don't, like, push any sort of limit, but, like, it does not break. So this is getting at this thing of, like, and everybody loves them, and the value stays really high on them because, like, you do not need to question if this thing is going to keep working or not.
So there's this quote that you had one. I think it was like the last time we talked, basically. But you said, I won't forget this. You said, "quote I'm a college dropout and I just build stuff." Like,
yeah.
I think you have like a really good pragmatism to you, where you basically just like you like to build things that work, and you like to see them built, and it's less about let's sit in a dark room and come up with the perfect blueprint over, and then hand that off to the like manufacturing team that needs to go put it in that machine behind you. It's like,
yeah,
no, it's more of like, you're going to build things if you're here.
Yeah. Yeah. So this is definitely, I mean, this is what informs it in my life is like, I just like, I run that machine. Like, I am the one building the things. And like, in my case, like I have built, like, it's very like I design and engineer through intuition, which is not, and maybe people won't like this sort of like concept. Like, most engineering is very detached. It's strictly like this is what the numbers say. Like, but there's not really a great intuition of like how does that translate into the actual thing. And this is not across the organization. This is like how I function internally. Is I could see some parameters and like quickly sort of map of like, okay, what this amount of like mass flow, all right, well, the air is like roughly the size. Like, you just have an instant sort of intuition of like, okay, the thing would probably be like this. And when you imagine, like, in my case, like, imagine handling the thing like that, like, what's a like, oh, if it's going to be this way, like, that's going to be too flimsy, and it is these like little things of like, the whole vehicle is a culmination of all these little parts like that. And so just having that sort of constant gut check is, I think, how you get there. And so, yeah, this is where, maybe this, like, I didn't go through the classic engineering path that, like, I just went straight to building airplanes. I had a phenomenal mentor who really instilled this notion of, like, really build things well. But you, like, the more common method is, like, all right, you go through, like, mechanical engineering, you get your mechanical engineering degree, you barely spend any time in, like, CAD, you're learning how to do FEA and all this stuff. But you're not, like, spending enough time, like, making things. Like, ultimately, the thing, it's, like, needs to translate to the physical world. And it's going to be like really different from coming with a place of, I used to build engines out of cars, and again, I built airplanes as a kid. Like, knowing like if you put this thing there, this is going to be miserable to assemble this thing, and now it's like going to be expensive and annoying to fix. And now that translates into the whole organization of like, now you can just imagine the mechanic sitting there trying to fix this thing and like, oh, what a nightmare. Oh, this engine is especially expensive to fix now because of like the people made it weren't really thinking about how they're going to interact. And that also ties in with like more of my philosophy, which is this is like what industrial design is as well. Industrial design is sort of it's the engineering of human interaction with stuff, like physical things. Yeah, that's why again Apple products are so nice. Is like they have just thought through like every level of the human interacting with the thing. It's really taking this into account. And that's also how I think, across the whole organization, when you're making this stuff, really think about, like, you're a human, there's other humans, they are working with this thing. That's actually a kind of human-centric approach on it. And that's what translates into the thing being, like, you just imagine, like, all right, you have a bunch of these planes out there, what is the mechanic, like, when the plane is going in for maintenance, like, are they just, like, loving the fact that there's just this one like piece and they just like slot the thing in there like, oh, perfect. Like we started to have this like we have like modern airplanes have FADEC where we have like electrical control systems. Like sweet, there is a magical box that we plug into this thing and we replaced billions of like little actuators and valves and mechanical old analog stuff with like, yeah, here is like magical computer box. And it's just like elegant, simple. Now you need to make magical computer box super reliable and like for it to be implemented, like, yeah, it needs to be better than what it's replacing. But you just end up like, that is an incredible experience to the work of that thing. Like this always being top of mind for everything that's being made, I think is just very important. So, yeah.
Yeah. And you're also a person who builds really fast prototypes. Like I think like that was one of the things that I thought was coolest was when I went and like checked out your factory or whatever. Like you, let me like set the scene. You basically you're in San Francisco. You turn down an alley. Like there's basically just like it sort of looks normal. Like it looks residential. There's like houses. There's like a person hanging their laundry up in the window. And then you turn the corner and there's like a supersonic engine sitting on the ground.
Yep.
It's amazing. Like you guys built that so fast and you like did it just like in the middle of San Francisco. Like that's part of your DNA too is prototyping,
and I guess
right?
this ties into again of I find it quite hard to sort of break the engineering mindset on this stuff of like focusing on the right things with when you're making something is like, what are we trying to prove with this particular thing? And it's like, all right, the high level, so like the prototype we made, it was like a month and a half from like team was here for like sort of first draft on parts to the thing was running, and then 2 weeks after that, so 2 months total time from like idea to like sweet, the thing is fully running and demonstrating exactly what we were, like it was exactly what I'd predicted for performance. There was like 2 months time, and it was because we weren't spending like this thing isn't it did its job, like we'll iterate another one. We didn't need to focus on like what is the bearing life going to be like. Do we need to do all these optimizations? Like, no, actually, we can just say like the bearings on this one, like it's going to run a total of like a few minutes, its whole life or something like that, or maybe a few hours, whatever. Cool. We don't need to do a whole like analysis of the bearings. Where in more like if you're sort of typical aerospace thing, it's like, oh no, we check all of the boxes on this. And it's the art of knowing what does and does not matter on a particular thing. Like, that is critical for the flight one. Like, yes, we need to know when, like, we need to eventually work on this sort of reliability. But in the meantime, it's like, all right, well, key components of this is like compressor efficiency. All right, we're squeezing air, electrically. Like, this is sort of a new way of doing this. We're running combustion. We want to see how much thrust we're getting out of it. Like, all right, what are those pieces? I did a little bit of like a part spin special on this of like, okay, we didn't need to like develop a clean sheet electric motor. I used like a race electric motor for a thing. Like, sweet, that was like $13,000 for the motor and the inverter. It's definitely not flight weight, but like driving this component, the compressor, it's like, all right, we didn't need to make our own compressor on this one because I found a Top Fuel dragster, supercharger that was like pretty comparable. It was like really lossy. It was like terrible. It's like 50% efficient compressor, but we can account for that. Like, all right, we're not developed. Like, this isn't the flight engine. We don't really care about the compressor efficiency there. We can account for this in other places. It's like, all right, and then all right, we have to make the combustor and all the control components around it. But like, sweet, we at very little time and money proved the core thesis. Now the system that I'm making right now is like, now I'm making my beautiful, elegant, like this machine is going to be, put to work of like making our custom compressors where now we can go into that next step of optimization. And yeah, so like that's, and still it's not going to take that long. Like, because we know exactly what things do and do not matter now. Yeah. So yeah, engineering through intuition is sort of an odd, is not too typical, but like really focusing on going for the things that matter in this stuff. So
I love it. So what, I think like my kind of like final thread of questions is basically just, you have been at this for how long now? When did you guys start working on this?
For like, I guess formally, this like long
it's
evolution.
Been percolating for longer. Yeah.
Yeah. Like this all came out of a hybrid. The initial program was I was making a private jet that could be a cost parity, like regular private, like subsonic private jet. That could be a cost parity with airliners. I started, I had the insight on that around 2019, 2020, I think 2019. And I had the Supersonic, like this fundamentally new adaptive engine was possible because it was because I was spending all my time on this prior work. That was, late 2021 that I realized that. It just came from me thinking like the hybrid stuff I was making is like, what if I made a fighter jet? Or like, how could I use the thing?
Nice.
Like all of this, and I do think it's just kind of funny, like all of this is happening in a sense because like I knew I was never a good enough student. I would never be allowed to fly a fighter jet. And like at a very young age, truly since I was like a teenager, like I knew I would never be allowed to do that. But I always knew it was like, well, I could be the one that makes the fighter jets. I could definitely fly it then if I'm the guy making it. So like it's always just been this sort of goal of like, all right, figure out the thing. Like at the end of the day for me, it's just like I love flying and like cool machines and going fast and stuff like that. Like I'm doing all of this work to build like a whole new Boeing just because I want to putt around. And I'm not their fighter jets. I don't like their fighter jets. Those aren't good enough. Like I want it to be the cool thing that I know we could make.
My fighder jets.
My fighter jets. Way better. And so start all of this so that I could just have my fighter jets. So
I love it. And that was where that's like 4-ish years ago, and you're like, so at that point, and well, maybe it was even like sooner, maybe it was 2021 that you really started like really thinking about the electric adaptive thing, like how, but even if those dates are wrong, anyways,
October 2022 was when I raised around from lower carbon. And I think it started on the engine 6 months, I started building the adaptive engine, like around 3 to 6 months before that.
Okay.
No. So yeah, that's
yeah. Okay. So let's say that like, so you started, like you really started like in earnest on this thing sometime in 2022.
And like, honestly, March of 2023 is really when it.
Wow. Okay.
My first, this has been like, I've been one man banding this thing for a long time. I got my team. I finally had like an actual team of other, aerospace engineers. They started March 12th, 15th, so around there. And I started talking to them in November, December. So yeah.
Okay. So yeah, I mean, it hasn't been long at all. Like you've really been at this for, and my question is, since you started working on this, I imagine that, you had this intuitive idea in your head of like how this could end up. Like, what do you think, like, what is the main progress that has happened from that original idea? Like, what are the main things that you feel like, okay, we really nailed this. Like, I really validated this part of the hypothesis. I validated that part of the hypothesis. But like, there's these other parts that I still have to do a lot more testing on to really like know it's going to work for sure. Like, how far along that journey do you think you are?
I mean, the big one is, it is not just me now. Like, it's just me here. It's Saturday at the shop. But like, it's the team. I have like, I had a test. I have like people now. So we're going to be 9 of us soon. Everybody far smarter than me at any one of these given like things. So that was the big change of like, I laid the groundwork on this, and now we have like instilled the build design build test repeat. Like I have like those are literal people in the team now. And it had to be just me sort of running this loop. There is now like, we have these functions built in, like, and we don't really, like, we can get all the way to our flight engine on the propulsion side of things. Like, and we don't need more than 9 people. Like, that's, and it's really just like 6, like, it's having, the fewer brain, you have like many fewer losses when you have sort of fewer brains to like go between on this stuff. So it's like, if you have a really great person, so that was the thing that we've like fundamentally built there. Next steps is like, so I went through the whole process, like the engine that I had, like that was my sort of brainchild for the prototype one, but now, I can only, go so far with the stuff where like now we have the real team, like we're making our first, like this is like the team's baby now. And it is just going to be a sight to behold. Like it's a work of art. And now, I've seen the cycle, we've gotten it through. Now I'm going to be repeating this again on the airframe end. So this is sort of the next. So I sort of call this like, ultimately the pillars of our company are engines, airframes, and operations. So we started with the engine, and we've proved like I've gotten firsthand like, okay, this is, and I had run small businesses before, again, motorcycle stuff, but nothing like this. So, learning how to run a team like this, this has been like, a lot of this is like really what my time is spent is like learning how to run this sort of organization. So, all right, engine, we figured it out. I feel like I lucked out in a sense of just having such incredible people. Then we go, like, now I have a good model of, like, I'm replicating this again for the airframe organization. This is our next step. Like, okay, we're aiming for roughly March. We're going to have our flight engine, and, it will run, like, we know how this is the thing that we're going to bolt on the airplane. And so I'm just now in the, like, repeating the cycle of getting my, got an aerodynamicist, who's just starting out in some of this work, and we're going to go through the process again now. Like, okay, what is the airframe that goes this going to be? I can do my first order math. Like, again, I'm pretty sort of like my utility in this is like I can stitch it all together. So yeah, that's now happening. And I think that's probably going to be around like 12 people if I had to bet. I had to guess 12 total for the airframe team. And at that point, like, okay, we have our engine, we have our airframe. We have a thing that like should be able to fly now. And this is the final piece on this is going to be like, it's at operations is like really critical. It's like, getting, working with NASA or DOD, like FAA, like getting approval on these things, dealing with that in the field. Like that's the last piece. And like in each one of these, we're laying the groundwork. Each one of these verticals will then be the foundation for like, when you imagine this future airline thing I described of like, the seeds of all of that, were planted now with, it's like, yeah, the team that's like learning how to run this thing out in the field, we're learning how to like support the aircraft and stuff like that. Like that was all, work that was done now, that'll translate to like years down the road where an airline or charter or something like that. Like, yeah, we at least got a few reps in early on. So it's like sort of the last piece. So yeah, I've established the pattern, completed the pattern, and now, replicating this a few times in like different components. So
very cool. Yeah. And so, okay, final last question. So your sort of like engineering intuition that you built up, you said was basically not something that they really teach in a class. Like there's not like one course, one degree program that you could take and then acquire the knowledge that's in your head. So how would people go get it? Like if a person wanted to do something similar to what you're doing, what would you recommend? How would they do it?
You have to be doing it a lot. I think it just comes from like, certainly it's easiest. I think like there's such an inclination. I was sort of lucky in the sense of like, I loved this as a kid and I was allowed to just forever build things as a kid. And, like be it like having, for other people I can imagine like, I don't know, have a go-kart or something like that or like, but you need to do it. You need to be the one that's like physically building this intuition of like, you're turning the wrenches and doing all this stuff. Again, I lucked out in the sense of like, I was already doing that, but I had this mentor that I mentioned, I met through like model aircraft. He was American Airlines captain. So I think actually RC aircraft, and I actually have another founder friend with the same thing, good mechanical engineer. RC airplanes are like a pretty good way to do that. Actually helicopters, but that's sort of like, it's all of the same pieces and you can start to like, it's like in an attainable way at a young age. So yeah, I would say starting with that, similarly, like it's good if you're in high school and you alone pulled an engine out of a car, like I would do like, like I wanted big turbos in my car. It's like pulled the engine out of it. And like, this is the other way I was able to get away with like having nice like German things. It's like, well, I was the mechanic. There was no like, I still to this day am like cringe the concept of like going to the dealership to fixing. Like, no, I fix these things. Like I care more. And actually, I just use that word. I think the other really critical component in this is, above all, and the thing that I look for is like you really care about it. That is one where it's like we see this in a lot of ways. Like there's a certain earnestness that you're just allowed to be, like being cool in a sense is like, oh, you don't care too much, right? Like it's like, oh, it's sort of detached. And like, interestingly, I think that even plays out in building stuff of like, no, like care to an irrational degree about like how nice this thing is. Like just being okay with like having that of like, it's like, no, but I want this to be this way. Like, even like, I get that like maybe these things are all, the engineering mindset of like, no, this is what are you talking about? Like this piece of metal is the same as this other one, but like, yeah, but this one's ugly. I don't know. It's got like,
yes,
got a little bit of corrosion on it. I don't like it. Just that kind of care, like having that extra bit of care, I think is really, that's the trait that I look for of like, which, there's many flavors of it. You can say like obsession and things like that. But like, again, just really caring. I think cultivating that is critical. And, it's also just like spending a lot of time doing it, right? Like there is, like, that's how my version of this, like the way that I guess I sort of built the intuition is that I have, you eventually like experiences such I have done I've mapped all of the corners of wrong things you can do. This is the best way to do it. Is like, make sure that you did all of it and saw all the failure modes. This is going to take you like a solid decade to experience all the failure modes. But when you do that, you at least get to this point of like, okay, I've seen this before. And so you need to make sure that you also learn from those. It's not enough just like, oh, I'm out there failing. Like, no, you want to fail in a productive way of like, God, I wish I didn't do that again. Like really knowing why. So yeah, other ways to sort of build that up. But,
yeah. Awesome, man. Well, thank you so much. This was awesome. This conversation rocked. I guess where should we send people? What should they apply to Astro Mecha?
yeah, I do. We do. I think great people is like the core of all of this stuff. So finding more like minds is going to be critical. There's nothing right now, but like Astro Mechanica is the company. I'll maybe by the time this is up, I'll have like something on the website for I'll have like probably hiring at Astro. Hiring at Astro Mecha. We'll make
it happen. It happened. It started here.
yeah, we'll do that.
Nice.
Maybe I'll make a LinkedIn or other things like that for the stuff. But yeah, if this resonates, definitely would love to find like some sharp minds on the stuff. So yeah.
Alrighty. Well,
Cool.
Thanks so much for joining us.
Yeah.
See you, man. See you.